Today we're going to be talking about linear first-order differential equations. And these are wonderful differential equations because they fall into this great category called things we can solve. So there's actually this wonderful technique we're going to be talking about in just a few minutes called integrating factors that lets us solve these problems. Woohoo! You know, there's a lot of times when we look at a differential equation, we're like, it's not so clear. But this will not be one of those times. Wonderful things. Well, let's begin. So let's start by talking about what we mean when we talk about linear. So we say a first order differential equation is called linear if it can be written in a very specific way, namely as y prime plus p of x times y equals q of x. So in other words, there is some way for us to put it into this nice form. So again, our key word for today is linear. So today's topic is brought to you by the word linear. Well, let's look at some examples and see, all right, where's something where we have something linear, where's something where maybe it's not linear. So here I've written three differential equations. We can tell they're differential equations because each one of them involves a derivative. And let's talk about which ones are linear, which ones are not linear. All right, so the first one, y prime plus x squared plus e to the xy equals cosine of log of x to the fourth plus 1. Okay, great. Is it linear? Well, the key is to say, look, linear has a very specific form, right? It's this y prime and then plus p of x times y, and there's p of x can be any function of x you want. It doesn't have to be a nice function, any function at all. So it can be crazy. And you might say, well, x squared plus e to the x isn't that crazy. I know, but I'm just saying it doesn't have to be, 5 or x plus 2 or something. It can be very exotic. And again, same thing with q of x. And we look and say, yeah, look, it's of the right form. You have this p of x term here, this q of x, everything fits. So we say, yes, this is something which is linear. Good. All right, let's go to the second example. You have e to the y prime equals x squared plus 1 e to the y. Linear or not linear? What do you think? Now, you look at it and your initial thought is, aha, this does not look like that. So it must be that it's not linear. Except there's a key word here. This word can. It can be written in the form. So now the question is there a way for us to manipulate this expression so that we do have it in the right way? And, there's something we can do, which is called natural log of both sides. And if we do natural log of both sides, what do we have? Well, we'll have y prime will be on the left-hand side, and remember, product becomes addition. So that'll equal log x squared plus 1 plus y. And now we can move this across, and so we say, look, this equation can be rewritten in the form y prime minus y is the log x squared plus 1. And that is exactly the right form. You have y prime plus p of xy, where p of x in this case is just minus 1, but that's still fine, equals some function of x. So, is it linear? And the answer is yes. This is definitely linear. Good. So, keep in mind, things may not necessarily be put into the right and cleanest form. In fact, that's oftentimes one of the things that happens when you're looking at problems, is things get obfuscated. And you should always say, hey, wait a second, is there a nicer way for me to write this? And if the answer is yes, do it. Write it in the nicer way. Because our goal is to say, look, let's make life easy on ourselves. We love ourselves, and we want to take care of ourselves. All right, the third example. Y prime plus e to the y prime equals x. Is it linear? And now, after the previous example, it's okay for you to pause and say, I'm not sure. And in this case, the answer is no. In essence, you see how there's a y inside of this exponential function? You say, well, great. How do you get it out? Well, you could use a log. But once you get that y out, you put y prime inside of a log. And so no matter what, there's no way to free it in a natural, clean way. So this is something which is not linear. And there's no hope for us to get it to our nice expression in any reasonable functions, p and q. But take a look at this expression here. Could we solve this differential equation, and how would we do it? We can solve it. Why can we solve it? Well, if you look, everything involving y's are on one side, everything involving x is on the other, and really we could say, hey, this is 1 plus e to the y, and the y prime thinking as dy dx, dy equals x dx. In other words, this equation is separable. So we say, aha, something can be separable but not be linear. And it's also true the other way. Something can be linear but not be separable. So for instance, up here, good luck trying to separate that. So separable and linear are two different ideas. And occasionally they overlap, but not too often. And so we have, okay, great. So we have a wonderful technique for separable. And today our goal is to say, hey, we have a wonderful technique for these linear things. Now, on a side note, because, I love to go off on tangents, it's why I'm such a good calculus teacher. Where does this linear idea come from? And because you're going to hear it a lot as you go through mathematics. And so when you hear the word linear, what are we talking about? Now, you might see the word line inside of linear. That's not such a bad thing to see. It really is about things which are flat. And ultimately, it comes down to sort of two ideas. And namely, linear, and in particular, when you think of linear, we think of linear combinations, really says, look, we can do two things. We can scalar multiply, which means we can multiply by a number, and we can also add. So if we can do combinations of scaling by a number and adding, then we consider that a linear thing. And we like operations that respect these types of operations. So we might have heard the phrase, derivatives are linear, integrals are linear, because they say, look, I respect addition. I respect multiplying by a number. Now you might say, well, wait, these don't look like numbers. These look like functions here, right? These p of x's and q of x's. And we consider the numbers from the perspective of our dependent variable y's. So from the perspective of y, we say, well, look, you have y prime and y, and these are combined together in nice ways. Namely, we're allowed to scale those values, and we're allowed to add. And great, so that's what we can do. Now, our fact for today is the following. It says, look, if you have a first order linear equation of the form we've talked about, and we have an initial condition, so y of a equals b, then there is a unique solution. This is our it's a beautiful thing. We have an answer. We're guaranteed to have an answer. In fact, we have an answer basically as far as we are able to go with the functions p of x and q of x. So as long as those functions p of x and q of x are nice functions, we're able to extend our answers. Now, how does this work? How does this fact work? And the way this fact works is actually really simple. We're going to produce a solution. And so that's how we know a solution exists. You say, look, here's how you find it. And the way we do it says, look, it has to satisfy this particular solution. So it's a unique solution. All right, so that's our goal. We're going to produce a solution to this kind of a differential equation. And so let's talk a little bit more about how we do that. So the basic idea, and it's really such a simple thing, is it comes down to the following really easy question. What is easy to integrate? And the answer is a derivative. It's really, really easy to integrate a derivative. And so what's an example of that? Well, we know, for instance, if we take the derivative of some random function, I don't know, arctangent, that seems pretty random, we know that's 1 over 1 plus x squared. Well, now that I know what the derivative of arctangent is, I can say, well, look, I could integrate both sides, and I come to the conclusion that arctangent of x is equal to the integral of 1 over 1 plus x squared. So if I know something as a derivative, by integrating, I get a nice answer. Now actually, of course, there's that little extra fudge factor, that plus c, that comes into play. So we say, okay, great. Since we know that it's easy to integrate a derivative, let's take this and make it part of a strategy. And the strategy is, let's make the hard part of our equation look like a derivative. Now you might say, well, which part's the hard part? Well, namely the stuff that involves y. That's our goal. So we want the stuff involving y to look like a derivative. Then we integrate that part easily, and then everything else only involves x. And we say, okay, we integrate that, and now life is good. So let's illustrate this idea by an example. So here we have this lovely example, has a nice couple of parts here, and we'll start with part A. What is the derivative of x squared y? And when we talk about y here, we're thinking of y as a function of x. So you say, okay, well, what is that derivative? What do we need? Well, because we have x squared multiplied by y, we really have two functions multiplying together. So we say, all right, so the rule that we need is product rule. So one way the product rule works is, okay, we have our two pieces, and we'll say, leave the first alone, so that'll be x squared, and take the derivative of the second. What's the derivative of y? Yes, the derivative of y is the derivative of y. So we denote that as y prime, or you could write it dy dx. I tend to write y prime a lot, mostly because it's faster for me, but you could also write dy dx. Okay, now we're not done yet. See, we take the first times the derivative of the second, and add to that the derivative of the first, 2x, times the second. There we go. That's it. That's part A. We're done. Great. Now, part B. So what does part B ask? It says, find y given that x squared y prime plus 2xy equals 5 halves x to 3 halves, and y of 1 equals 2. Now, at this point, you're probably like, wow, Steve's really throwing us into the deep end. Wow, come on, Steve. Slow down, slow down. We haven't even talked about how to solve these kinds of problems. Now you're saying solve it. How can we expect to do that? Well, this comes back to our kind of one of our philosophies that says, when we have multi-part problems, there's often connections going on, which is to say, part B probably has something to do with part A. And we're like, oh, yeah, okay, all right, let's take a look. We know the answer to part A, it's right there. And we look at that and say, whoa, that looks awfully like what we see right there. And all of a sudden, a light bulb comes on. Boom! We see something. And what is it we see? Well, what we see is that we can rewrite this problem here, finding the solution, as saying, well, look, the left-hand side is really a derivative. It's the derivative of x squared y. And the right-hand side is the right-hand side. So, but again, the key is the stuff involving y, we put into a derivative. And then everything else was like, great, well, it's just stuff with x. Now, what comes next? Say, hey, we know how to integrate derivatives. So we're going to integrate both sides. So integrate both sides. And let's see what happens. Well, what do we get? The integral of the derivative is the original function, x squared y. All right, integral of 5 halves x to 3 halves. Now, you might be able to do it in your head, and if you can't, that's okay. So the 5/2, and then there's going to be a number here. And when you have power of x, you add 1. So 3/2 plus 1 is 5/2. Oh, that's rather interesting, convenient. And don't forget now to take that new power and flip it over and write it down. So that would be 2/5. And oh, that was very convenient. Almost like it had been planned. Because it was. All right. So it's x to 5/2. Are we missing anything? Plus c. Plus c. Okay. Now, if we want to get y by itself, say, hey, that's no problem. We take everything, divide by x squared. So x to the 5/2 divide by x squared would give us x to the 1/2, because 5/2 minus 2 is 1/2, and then plus some constant c, divide by x squared. And this right here is not our answer, but we should pause and say, yay, we've made progress, because this is the general solution. All the solutions to our differential equation look like that. Now, why is it not our answer? Well, we're not after a general solution. We're after a particular solution. So we need to satisfy our initial conditions. All right, so let's do our initial conditions. We need to have that when x equals 1, that y equals 2. So we'll have 2. 1 to the 1/2 is 1 plus c over 1. All right, well, that's not so hard to solve for c. That says we need c equals 1. And so our real answer is x to the 1/2, which, well, we can go ahead and write that as square root of x plus 1 divided by x squared. And life is good. Life is great. We solved it. We have our nice, beautiful answer. Okay, so that's wonderful. And that took advantage of the fact that said, hey, our left-hand side looks like a derivative, and life was good. Now we come to part C. Let's talk about part C. So, it says, look, find y given that we have xy prime plus 2y equals 5/2, x to 1/2, and y of 1 equals 2. And we say, ha-ha, wonderful. And we look at it and say, oh, wait a second, xy prime plus 2y, that's not a derivative of something. You can try, and it's not a nice derivative. And so at this point, we're like, oh, our wonderful idea crushed. Oh, what can we do? But again, we say, hey, this is a multi-part problem. And we look at part C and say, you know, it's really, really close to part B. How close? Well, if you look, you say, hey, if I multiplied everything by an x, it becomes part B. So we say, oh, an idea, another light bulb, boom, has just turned on. So we say, look, multiply both sides by x, and that's helping us rewrite our differential equation. And then we say, aha, now it's part B. And so it's the same answer. So what was the thing that happened here? Because this part C is really kind of illustrative of what we're after. So what we want to do is we want to make the left-hand side, the part that involves the y, look like a derivative. And if it doesn't look like a derivative yet, we say modify it appropriately by multiplying by the right thing. We're not going to multiply it by an arbitrary kind of function because that probably won't work. But if we multiply by a correct choice, a function with the right properties, that'll give us exactly what we will need, and that'll help carry us through. And so we want to sort of get to the stage where we can say, okay, we need to multiply both sides by the right thing. What is that? And so that is where we're going next. And it has a name. We call it an integrating factor. So why do we call it an integrating factor? Well, sort of two pieces are coming into play. First off, it's a multiplicative factor, so we're multiplying by something. And the real goal is to make it something so that it helps us to integrate. So that's why it's an integrating factor. It's something which helps us get to what we want. So in particular, we say the following. An integrating factor is some function, rho of x, such that when we multiply everything by that rho of x, the left-hand side can be integrated. It's the derivative of something. All right, good. So this is our key tool for today. So we say, all right, well, let's think about what will be true. So we've taken our equation, differential equation, and multiplied everything by rho of x. So these are the same differential equations. We say, well, look, we want this left-hand side to be the derivative of something. But we actually have a good idea of what that something should be. Because notice, you have like a y prime and a y. So you said, oh, well, here you took the derivative of y, and here you left it alone. So you remember, when you think about the product rule, we say, okay, take the derivative of one piece, leave the other piece alone, and then vice versa. So that says, oh, well, since I took the derivative of y in that part, the other piece that's in front of it, that's the part that we left alone. So what we really need is that this left-hand side needs to be the derivative of rho of x times y. So this integrating factor times y. So that's what we need. How do we make sure we choose the right rho of x? Well, here's the thing. We can actually take that derivative, right? Rho of x times the derivative of y plus the derivative of rho of x times y. And then we can compare it to what we have. And now we start doing our, okay, matching kind of thing. We say, well, look, they both have rho of x, y prime. Matching, great. And then we can say, look, in this next part, they both have y, more matching. And then in the last thing, it's like, oh, these don't quite line up. So we say, okay, so what we need to have in order for this to work is that this rho prime piece needs to look like rho of x times this p of x. As long as those things line up, life is good. All right, so that's our new challenge. Well, notice we can take that and say, well, that's the same as saying rho prime over rho is our function p of x. And why is that nice? Well, because the left-hand side is really good for integrating. Because we have the form, a function downstairs, derivative of that function upstairs. And whenever you see that, that suggests the log. So when you have a function downstairs, derivative of the function upstairs, that, when you integrate, becomes log. So you do the substitution. U equals rho of x, du equals rho prime of x. So we have log of rho of x, that's the integral of the left-hand side, equals the integral of p of x. Or, want to solve for rho, so we use the exponential function, which means e to the. So we say that, look, this integrating factor, rho of x, is e to the integral p of x. Great. And that's it. So that's the beautiful part. So we have this nice integrating factor. We say, look, multiply both sides by this. Now you'll see there's a comment here at the bottom that says we can set our constant from integration to 0. And at this point you're probably thinking, wait, what? We get to force our constant to be 0? Don't we have to keep track of them? And wait, which constant? Where? And so here, let's step back and say, well, normally we'd have there a plus c. So when we talk about we can set our constant integration to 0, this part here, this is what we mean by we set this equal to 0. Now, you might feel a little bit like, that seems cheating that we've been told, keep track of the constants. Why all of a sudden can we just be like, just set it equal to 0. That's not a problem. What? How? Why? What? So let's talk about what that plus c would do. So we can actually follow it, right? So suppose we allowed there to be a plus c. So you'd have log of rho of x is equal to the integral of p of x dx plus a constant c. And if you do e to the on both sides, you'll get your rho of x term over here. And on this side, well, you'll have your e to the integral of p of x dx. That's the same thing as the exponential function of the integral of p of x dx. And then, remember how this works. This e addition becomes multiplication. So you have e to a constant, and e to a constant is a constant. So we can write it as c. So the thing is that by choosing a constant here, you essentially change your rho of x to a constant there. Now, why don't we care about this constant? Well, remember, it's a multiplicative factor on both sides, which means everything is getting multiplied by c. So you would have a c and a c and a c. So everything has that multiplicative factor of c. Well, since everything has it, what can you then do? Well, you say, oh, let me just cancel that off. And now you have the same differential equation as before. And so that's why we say, look, at this particular stage in the process of solving, we can choose our c to be anything we want. And so we often say, let's choose it to be the easiest thing for us to work with. So that's why we say we're going to choose c t equals 0, because it doesn't have an effect on the solution. Now, as you move forward, there will be another step where we have another integral to do. So this has several integrals that you have to carry out to get your answer. And in that other step, we do need to have our r plus c. So it's important to remember when we need to have our constants and when we don't. Don't confuse it. So, all right, good. So let's put this all together and talk about our method. That's really not the method, that's sort of the tool that we need to carry out the method. So here we go. So initially, call it step 0, and the reason I put it as 0 is you may not even have to do it. And it says you're after solving it, so make sure it's in the right form. So we're going to write it as y prime plus p of x y equals q of x. So we might have to move things around, might have to do some division, might have to get a little bit more exotic. But the point is, we put it into the right form. All right, so now let's suppose we have our problem in the right form. First step is, let's find that integrating factor. So we compute rho of x. And once we have things in the right form, it's very easy to do, right? We say, look, we know where that p of x is. We're going to integrate it. And after we do it, we take e to that, and that's our integrating factor. The next thing is you say, okay, multiply both sides by this integrating factor, and the left-hand side will be nice. The right-hand side will be something. Hopefully not too bad. Really, the key is on this problem and this method is to say, focus all your energy to make that left-hand side nice. Don't be surprised if the right-hand side isn't the nicest thing you've ever seen, but that's all right. That's all right. On a side note here, we should point out something really kind of nice going on here, is that if you look at this, this has sort of a built-in check. Because you might say, well, I wonder did I get the right integrating factor? And the way you check it is to say, well, look, it is the right integrating factor if the derivative of this expression, the integrating factor times y, is that new left-hand side. So you can carry that computation out, usually fairly quickly. And if it's not, whoops, mistakes were made, quickly go back and check your work. And if it is, then you like, yes, for sure, I nailed that integrating factor. High five! Woo! Yes. All right, so that's just something to keep in mind. Okay, so we found our integrating factor, we multiplied both sides, we said, aha, life is good. We integrate both sides, and this is where we have to keep track of that plus c, and this is where, hey, I have a derivative, easy to integrate. And now we're basically in the home stretch, which is, hey, I need to get y by itself, so divide by rho of x. Be careful here. Remember to divide everything by rho of x, including the plus c. So it's not just the first piece that gets divided by rho of x. Everything gets divided by rho of x. And the last step is an optional step depending upon the type of problem you're working on. If you're looking for a general solution, well, there's your formula. If you're looking for a specific solution, well, use that information with the initial condition to solve for C. Now, there's a piece of advice that's given in the textbook, and I think it's a good piece of advice, which is to say, don't memorize this. In other words, don't focus on the formula, rather focus on the process. And the reason is because it's easy to make a mistake, because you say, oh, well, what is rho of x? Oh, rho of x is this, and how do all the pieces fit together? It can be easy to make mistakes. So instead, just say, look, I'm just going to go through step by step in the process, and then I'll get the right answer. And so that's a great piece of advice. And in fact, it's a very good piece of advice in general. If you just learn formulas as though you were learning, ancient text and going on faith, well, it's easy to make mistakes and be led astray. But if you learn processes, you're much more likely to understand what's going on and make fewer mistakes. And more importantly, you'll be able to adapt to new situations. So, all right. So that's it for all of the theory. Everything else is practice. And so we're going to do a lot of practice. So by the time we do 4 or 5 of these, you're going to be like, okay, yep, I see how it's going. It's very straightforward. We're going to do the same things over and over again. And because it's one very nice, simple, beautiful idea. So, all right, let's start doing some practice. Here we go. All right. Find the general solution for the differential equation x squared plus 1 times y prime plus 3x times y equals 6x. All right. Where do we begin? What's the first thing we need to do? The first thing we need to do is to write it in the way that we can use the technique on. See, it's not written in the right form yet. What's wrong? Well, the problem is this x squared plus 1. We don't want anything in front of the y prime. We want 1. That should be the coefficient of our y prime. And so what we need to do is say, okay, let's change it so that the coefficient in front of our y prime is 1. So we do it by dividing. So we're going to divide everything by x squared plus 1. So we're going to have that y prime plus 3x divided by x squared plus 1 times y is equal to 6x divided by x squared plus 1. Good. And now we're happy. We're making progress because it's in the right form. So this piece in front of the y, that's our p of x. So the next thing for us to do is to integrate that. So the integral of 3x divided by x squared plus 1. So how do we integrate such a thing? Well, okay, it's not so bad. This is actually in good shape for us. It looks like we have a good substitution. If you let u equal x squared plus 1, then du will be 2x dx. Now you might be looking at this and say, oh, so close, so close. 2x dx, we were just 1x away. Well, but don't worry. You see, there's this new trend going on, and it's a state-of-the-art thing. It's called divide by 2. So what we can do is we can say, look, I can divide both sides by 2 and say half du is x dx. And now, like, oh yeah, we can do that. And that lets us do our substitution. So constants are easy to move around. That's the nice thing about constants. Well, it's one of the nice things anyways. And so we say, okay, well, what do we have? Well, we have the 3 here, and now the x dx is going to give us a 1/2 du. So there's a half, and then there's a du. Now that accounts for the 3x dx. We still need to account for the x squared plus 1. Remember, in substitution, everything needs to be accounted for. Well, all right, so there's means there's going to be a u downstairs. So 1 over u. So that's that's a nice integral. That's actually one of the integrals that we know, 3/2 log u. And remember, because we're solving for our integrating factor, our plus constant will become plus 0. So we're not going to keep track of that constant. We'll just say we don't need to worry about it at this stage. Now, we do need to put it back in terms of x. So we have, this is 3/2 log of x squared plus 1. Or if you like, that's the natural log of x squared plus 1 to the 3/2 power. Now, is this our integrating factor? And why not? It's not our integrating factor, but we're close. What are we missing? Well, we're missing e to the. Remember? It's e to this integral. And so we say, okay, great. So our integrating factor, I'll abbreviate that as IF, is going to be e to the natural log of x squared plus 1 to the 3/2. And almost as if it was meant to happen, that simplifies fairly nicely. X squared plus 1 to the 3/2 power. Okay, good. So we now take our equation, and when we say take our equation, this one, not the one we started with, but the one we used to find our integrating factor, and we're going to multiply both sides by x squared plus 1 to the 3/2, which means we're multiplying everything by x squared plus 1 to the 3/2. So it's like, you get an x squared plus 1 to the 3/2 downstairs. You get an x squared plus 1 to the 3/2. Oh, sorry, upstairs. You get multiplied by x squared plus 1 to the 3/2. You get multiplied by x squared plus 1 to the 3/2. Everybody gets multiplied by x squared plus 1 to the 3/2. So, all right, what happens? Well, the first term says, okay, we're going to have x squared plus 1 to the 3/2 times y prime. All right, that's pretty straightforward. Good. And then the next term, well, notice that this will have an x squared plus 1 downstairs, x squared plus 1 to the 3/2 upstairs. So that'll give us a 3x times x squared plus 1 to the 1/2. And then we have y. On the other side, very similar, we'll have 6x, x squared plus 1 to the 1/2. Because again, there's 1 downstairs, there's 3/2 upstairs. They combine together. We end up with x squared plus 1 to the 1/2. Now, the key here, and the reason this all works, the magic sauce, if you will, is that this left-hand side is the derivative of x squared plus 1 to the 3/2, our integrating factor, times y. And you can actually check, right? Leave the first function alone, times the derivative of the second, and then the derivative of this function, 3/2 comes down, x squared plus 1 to the 1/2, times the derivative of the inside, which is 2x, gives us 3x times x squared plus 1 to the 1/2 times y. All right. Good. So that's going to be 6x, x squared plus 1 to the 1/2. Now, we're sort of halfway through, because this really requires us to do 2 integrals. And we've done 1 integral. The other integral we have to do is we're going to integrate both sides. The left-hand side is a freebie, but the right-hand side we'll have to do a little bit of work. All right, well, so let's do our little bit of work over here. You'll see, hey, similar substitution, right? So you let u equal x squared plus 1, and du can be 2x dx. And we say, hey, that's kind of cool. You see, 6 can be written as 3 times 2. And then we have our 2x. So this becomes the integral. We're not going to use the 3, but the 2x dx will become a du. And this x squared plus 1 to the 1/2 will become u to the 1/2. So, all right, there's 3. Then we're going to have u to the 3/2 power. And then in front, multiplied by the reciprocal, 2/3. And don't forget that we need to have a plus c at this stage. Well, all right, we can cancel the 3's. Nice. And what do we have? Well, we have that this is 2 times x squared plus 1 to the 3/2 plus c. Okay, so let's see what we have now at this stage. We can say the following, that namely, that x squared plus 1 to the 3/2 times y, that's the integral on the left, is equal to 2 times x squared plus 1 to the 3/2 plus c. And the last thing to do is to divide everything by x squared plus 1 to the 3/2. In other words, get y by itself. And so if we do that, we'll say, well, that's rather convenient. Notice here, the x squared plus 1 to the 3/2 cancels, so we get 2. And then plus our constant c, divide by x squared plus 1 to the power 3/2. And that's our general solution. So all our solutions to our differential equations, this differential equation has that nice, beautiful form. What a great answer. And we're done. We're done. We made it. We got to the end. Wow. Great. Lovely. Lovely, lovely, lovely. All right. Well, good. Do you have any questions? The process is not so bad, right? We put in the right form, find our integrating factor, clean it up, multiply both sides by the integrating factor, do one more integral, and clean it up again. So let's just clean up, integrate, clean up, integrate, clean up. You know? Not so bad. Not so bad. Let's do some more. The more we practice, the better we get. We're going to get great. We're going to be amazing. All right. So find the solution for y prime equals 3 plus y times tangent of x, where y of 0 equals 2. All right. Great. Well, let's look at this. Now, is this a linear first-order differential equation? And it's not written in the right form yet, but of course that doesn't mean that it isn't. We have to say, well, can we rewrite it in a better form? And one thing we say, hey, you know, we could multiply this tangent of x through, and then we can rearrange. So if we did that, what would we have? Well, we'd have y prime, and then we'd have minus tangent of x times y is equal to 3 tangent of x. So again, we distributed that tangent of x through and then rearranged. Now we're in the right form. Exactly the kind of form that we need. And we also say, okay, well look, this piece right here, because we have the 1 in front of the y prime, so this is our p of x, including the minus sign. So keep track of that, right? We don't want to lose that because that's going to be important when we look for finding our form. Okay, so we say, okay, when we integrate our p of x, that's the integral of minus tangent of x dx. Now, tangent of x is one of our basic functions where we know the integral for that. We say, okay, so there's minus, and the integral of tangent is log secant. But notice this minus. What can we do with it? Well, what we can do is say, hey, the way we can think about a minus in front is that it's really like minus 1, and then we can put it into the log as an exponent, because constants go upstairs. All right, well, what does that mean? It means that another way to write log secant, or minus log secant, is log secant to the minus 1, which means 1 over secant. And if you look at 1 over secant, what do you get? You get cosine. All right, good. So that means our integrating factor is going to be e to the log of cosine, so which is cosine. All right, so we want to multiply both sides by cosine. So, all right, now we know. So we do that. So we're going to get cosine of x times y prime, and then tangent times cosine. Well, tangent sine over cosine, and so we multiply by cosine, the cosines cancel, so it becomes minus sine of x times y equals, on the other side, 3 sine of x. And this first piece, well, by design, and that's really the whole point here, is that this first part is a nice derivative. It's derivative of cosine times y. You can check it, right? It's cosine times the derivative of y, and the derivative of cosine is negative sine times y. All right, so that's equal to 3 sine of x. All right, and now the next thing for us to do is to integrate. So we're going to integrate both sides and see what happens. Well, the integral of the left-hand side, super easy. That's our motto for today. Make some integral at least easy. Integral of sine, it's just like we have to keep track of things. Right, because the derivative of sine is positive cosine. The integral of sine is actually negative cosine. So this is a common place where people forget the negative. But when you know it's a common place where people forget the negative, it makes you say, hey, hold on a second. Let me make sure I remember to check whether I need that minus sign or not. And don't forget you need a plus c. And now we're almost done. There's sort of two things left. Let's get y by itself. So we'll divide everything by cosine. So that says y would be negative 3, because the cosines cancel there. And then c divided by cosine. Well, divided by cosine is the same as saying times secant. And so that's our nice general solution. The last thing we have to do is say, but we're after a particular solution. So we say, all right, we need to have when x equals 0, that y equals 2. All right, great. So what happens? Well, so that says 2 needs to equal negative 3 plus c times secant of 0. And secant of 0 is 1. Okay, so 2 equals negative 3 plus c, or we have that c equals 5. And so we say, aha, now our final answer is negative 3 plus 5 secant of x. That's it. Good. Now, there's a lot of space here, and this problem was nice. So nice, let's do it twice. Because you'll notice something. Yes, this is a first order differential equation, linear differential equation, but it's also something else. It's also a separable differential equation. And so we can use that technique. And so it's the case that sometimes you can use multiple techniques to solve the same problem. Now you might be like, well, wait, do we have to? Are we going to get a different answer? And let's answer that first thing. Are we going to get a different answer? No, we will not get a different answer. It may look slightly different, but it'll be equivalent to what we already have. But it illustrates that, hey, there's some flexibility. There's room for us to explore and try different things. And so don't be surprised if it's like, oh, I could try A or I could try B. And so it's nice to see that, oh, both give the right answer. So here, this is separable, and we say, look, move the 3 plus y across by dividing, and this would be dy dx, we move the dx across, and so what we would have is dy divided by 3 plus y is equal to tangent of x dx. And all right, that's the separation, right? Because there's 3 steps. Separate, and then the next step is to integrate. So all right, we say, great, integrate both sides. Integrate. And what happens? Well, we have the integral of the left-hand side is a lot like a log because it's a log. So we get that this is log of 3 plus y. Integral of tangent, we mentioned it before, it's log secant. And then the last thing is plus c. Now, finally, we need to uncomplicate. How do we do that? Well, we say, look, use the e to the, right? Because we want to get rid of our natural logs. So, say, all right, e to the. So we get 3 plus y is equal to, now e to the log secant is secant. And finally, we have this e to the c. Now notice, because it's addition upstairs, it's going to become multiplication when we come here. And the other thing is e to a constant. Well, constants absorb constants. So e to a constant is still a constant. We'll just call it, well, we won't call it a new C, but these represent different constants, but the key is that they're both still constants. And finally, we say, okay, well, now I can move the 3 across, and we get negative 3 plus C times secant of x. And what do you see? What? They're the same. Exactly like what we thought would happen. So from this point on, solving for the particular solution, nothing changes, so we won't repeat that part. But the moral is, wow, look, sometimes we can do things in multiple ways. That's not a bad thing. It's a good thing. It's a lovely thing. So, wow, what a good problem. Fun problem. All right, well, let's try a word problem. So here we go. People love word problems, right? Okay, so what do we have? A 120-gallon tank initially contains 90 pounds of salt dissolved in 90 gallons of water. And brine, and by the way, when we talk about brine, think of it as like salt water. So you have this salt water, and it contains 2 pounds per gallon of salt. So it's very salty, and it flows into the tank at a rate of 4 gallons per minute. Now, what happens is that this tank is always sort of, as soon as new things come in, it gets stirred magically, instantaneously. That's the physics problems. Wow. But okay, that's not so surprising. Great. So it's well stirred, and now what happens is that the mixture, so we're talking about the salt water is flowing out of the tank at the rate of 3 gallons per minute. And the question is, how much salt does the tank contain when it is full? All right, now for this problem, we should probably tap into a little bit of our artistic side. So what do we have? Well, we have a tank. So we draw a tank. And all right, since we don't have to be too careful here, so look, here's our tank, and it's filled with our liquid. And there's a couple things going on. There's things coming into the tank, there's things going out of the tank. And so we should draw something that's coming in. So here's something coming in, and then usually we have something going out. And now let's write down what we know. So let's start at the beginning again. So we have a 120-gallon tank, and so that says our capacity is 120 gallons. That's just how much we can actually hold. That's not saying there's 120 gallons right now. It's just saying it can hold 120 gallons. And we know initially, so that's like, some initial conditions. So initially, we know that the amount of salt, so notice we're after salt. So we're going to actually introduce a variable here. We'll call S our salt at time t. So in other words, we're really thinking of this as S as a function of time. So initially, our salt at time 0 is 90. And we also say initially, there's 90 gallons. So it's not full. All right, so that's our pieces of information here. Then we say, look, things are coming in. Okay, so let's talk about our inflow, because that's going to be important here. So that's the first part of what's coming in. Well, what do we know? Well, it's coming in at the 4 gallons per minute of liquid. That's our brine. How much salt is coming in? Well, each gallon has 2 pounds. And okay, so if there's 4 gallons, each has 2 pounds. That says 8 pounds per minute of salt. All right. Okay, so that's our inflow. Now, how about our outflow? Well, that is the other part of our sentence. And so our well-stirred mixture is flowing out at 3 gallons per minute. Okay, so here our outflow is 3 gallons per minute, and that's of our liquid. And then we have some amount of salt is flowing out. So we should have to think about that. Okay, And what are we after? Well, the question is, how much salt does the tank contain when it is full? Well, wait a second. What does it mean when it's full? Well, initially, it only has 90 out of 120 gallons. So there's like this 30 gallons of capacity left. And if you look at it, we say, oh, 4 gallons are coming in, 3 gallons are going out, which means there's more coming in than going out. Since more comes in than goes out, we say, okay, that tells us something. Namely, it tells us that water level is going to go up, and more particularly says, oh, it's going up at 1 gallon per minute. Well, how many gallons do I have left? What's the capacity that remains to be filled? Well, it's 30. 120 subtract 90. Okay, so our goal, and we should be clear what our goal here is. So what's our goal? Is to say what is the amount of salt at 30 minutes. That's what we're after. All right, so what do we have? Well, we have the initial amount of salt, and we have information about how things are changing. So this suggests, hey, let's look at this from the perspective of differential equations. So we start by saying, all right, well, let's set up a differential equation formula. So we want to understand, how is the salt changing? Well, namely, when we think about how some things are changing, we say, well, what effects are there? They usually fall into 2 categories. What's causing the amount of salt to go up? What's causing the amount of salt to go down? So we should think about, okay, salt that's being added, and how is that changing? And then there's the salt that's being removed. And how is that changing? All right. Well, how does salt come in? It comes in through here. And we actually know exactly how it's being added. It's coming in at 8 pounds per minute. So this is really a rate at which salt is being added. So I say, beautiful. That's easy to do. That is 8. Now, how does salt get removed? Well, that's the other spigot down here. It's flowing out. So we say, okay, it all comes down to this part. That's where the salt gets removed. And so it's a question mark. Well, we can't put a question mark. So let's be a little bit more careful here. We say, okay, we're going to really nail down this question mark. We know the amount of the liquid that's going out. So we say, okay, so it's 3 gallons are going to leave at any given time. And now what we need to figure out, well, how much salt is there per gallon? So we're going to look at the ratio, which another way to say this is the ratio is measuring the concentration. So we want to say how much salt per gallon is there. See, right? See, if you have 3 gallons per minute, and we multiply by salts divided by gallons, you'll see, the gallons cancel, and so what it becomes is how much salt is leaving. So the question is, well, how much salt is there in this fluid? Well, remember we're saying it's well stirred, so it's just, you say, what's the total amount of salt in the tank? Well, the total amount of salt in the tank is just the total amount of salt in the tank. It's S. And it will vary depending upon when we're at. So it's S as a function of T. All right, well, how many gallons are in the tank? Well, now we say, oh, it's 90. Well, wait a second, that's how many gallons are in the tank initially, but the water level is going up. So how much water is there at any given time? And the answer is it's 90 plus T. So that captures how much water there is in the tank T minutes after this process starts. Say, okay, great. So that is how much salt is leaving at any given time. So we say, okay, well, wonderful. So this is 3 over 90 plus T times S. And now we have our differential equation. Wonderful. Good. Hard part is done. Now we just have to solve it. Well, maybe not the hard part is done, but one of the hard parts is done. So we'll rewrite this. This is the same as s prime plus 3 over 90 plus t times s is equal to 8. And this is really good. This is exactly the kind of problem that we've just been talking about. Almost as though we were anticipating we would need the method of integrating factors to solve this. So this piece over here, this is our p of x. So we integrate p of x, and we say, okay, what is that? Well, that's integrating 3 over 90 plus t. Whoops, I should say t, because we're thinking of our time variable as t, not x. So 3 over 90 plus t dt, which is 3 natural log 90 plus t. Again, we can choose our c to be 0. And then when we take e to that, well, the 3 can come in as an exponent. So this is really 3 to the log of 90 plus t cubed. Or, if you like, that's 90 plus t cubed. So this is our integrating factor. So we're going to multiply everything by 90 plus t cubed. So we're going to get 90 plus t, quantity cubed, plus 3, s prime, can't forget that. And here, we get a 90 plus t to cancel, so we get 90 plus t squared times s is equal to 8 times 90 plus t to the 4th. Well, the left-hand side, well, by design, that's the derivative of 90 plus t cubed times s. And we have the right-hand side. And from here, oh, why did I put to the 4th? It should just be to the cubed. I'm anticipating the next step, but that's dangerous to do. Slow down, slow down. We have plenty of time. Let's not make mistakes, because we want not just an answer, we want the right answer. All right, well, integrate both sides. And what will we get? We'll get that 90 plus t cubed times s is equal to, and now, all right, here we'll add 1 to the exponent and then divide. So that'll become 2, because it's going to become 4 up here, so 8 divided by 4 is 2. 90 plus t to the 4th plus c. Now, from here, we can actually solve our initial condition. So what do we have? We were told that at time t equals 0, s equals 90. So what do we have? Plug it in. So we're going to get 90 cubed times 90 is equal to 2 times 90 to the 4th plus c. Well, now if you look, what do you notice? Well, you see it's actually 90 to the 4th here and 90 to the 4th there. And you say, okay, so that tells us that c is minus 90 to the 4th power. A big number, but that's all right. It sometimes works out that way. So now we know c, and so we can find our function s. So we're running out of space. We're going to cram it in. We'll try to fit everything in here. So I'm going to put in what c is, and then I'm going to divide by this 90 plus t cubed. So we can say, look, our function s of t is equal to, now here when we divide by 90 plus t cubed, what you'll see is almost all of them canceling out with a single 90 plus t. So we'll get 2 times 90 plus t, that's this part here, minus 90 to the 4th power, which is our c, divide by, and then we have a 90 plus t cubed. All right, so that is our function anytime t. What do we want? Well, we want our answer, what happens at time 30. So our real answer, say, look, s of 30 is equal to, so it's going to be 2. 90 plus 30 is 120, and 2 times 120 is 240. So it's 240, subtract, and then we're going to have 90 to the 4th divided by 120 to the 4th. And you know what? We'll be happy with that answer. This is a great time to say, and the calculator can give us more insight about what's happening. We could actually clean it up a little bit without too much work, right? Because what do we see? Well, they both have, 120 to the 4th. I can't believe I did that again. 120 to the 3rd. Sorry about that. That looks really bad. Let's rewrite that. 120 to the 3rd. There we go. We could do things, for example, they both have factors of 3s. They both have lots of zeros. We could do a lot of cancellation. But at this stage, I would say grab your calculator, go for it, and see what happens. Okay, this is a pretty full piece of paper here. But if we step back and look at the process, then we say, you know what? Even though there was a lot that happened, no individual part was too bad. We said, look, we draw a picture to help us get an understanding of what's happening at any given time. And we make sure we translated our pieces of information to say, well, what does that mean? What does this 90 mean? What does that 2 mean? What does that 3 mean? You know, and once we understood that, we said, all right, set up a differential equation by saying how is salt being added, how is salt being removed, because there's not like any immaculate conception where it's like, oh, and suddenly salt was created spontaneously. No, either it comes in or it comes out. And once we understand how both those are accounted for, we understand exactly how salt changes. And then it's just a matter of working through the differential equation. All right, great. Well, not so bad, except I keep messing up that exponent. But, well, that's something for me to work on. And that's all right. We always need things to work on. Just slow down. Sometimes you get so excited to solve a problem, you lose track of things. Slow down. Take your time. Enjoy it. Enjoy the process, because we should enjoy it. It's math. It's enjoyable. All right, good. Whew. Well, let's try a different problem, right? We should try different problems. Okay. Whew. A lot less words in this one. Solve 1 minus 4x times y squared, and all that's times y prime equals y cubed. And you look at that, and if you didn't see the hint, so let's suppose we didn't see a hint, we would probably start to panic, be like, I don't know what to do, because this is definitely not linear. And so it doesn't feel like we're going to be able to make a lot of progress in solving this problem. But then there's a hint. It says, you know what? We're going to change this problem. So instead of saying, hey, let's focus on solving for y, we're really going to think of this as solving for x. And so we say, oh, are we allowed to do that? You know, that's not so clear. And the answer is yes, you are totally allowed to do that if they don't give you any additional constraints. But we say, okay, so we want to solve for x. And then we say, okay, well, how do we do that? So the hint is kind of interesting in that it asks a question in the hint. So we should start by thinking about this particular part. How would y prime and x prime be related? Well, how do we think of y prime? One way to think about y prime is it's the phrase dy over dx, which says, how does y change with respect to x? So that's what y prime measures, and we say, well, wait, if I know how y changes with respect to x, I can turn it around And then I understand how x changes with respect to y. And in fact, we do understand that because we can say, oh, that's really 1 over how x changes with respect to y. And we say, okay, well, what is this dx dy? Well, that's really an x prime. Oh, we say, okay, great. So we're going to take our differential equation here. We're going to replace y prime by 1 over x prime. And then we're going to look at it for a few minutes, and hopefully we'll have another light bulb moment come on and say, oh, I see it, I see it. So, well, we say, great. This becomes 1 minus 4x y squared times 1 over x prime, and that's going to equal y cubed. Well, we don't like fractions. Let's multiply that across. So 1 minus 4x y squared is equal to y cubed times x prime. And now we start to say, well, is this linear? And we're in sort of this strange phase, and namely, we're so used to thinking of things, where y always represents one thing and x always represents this other thing, that we gotta get our mind to think differently. In the following sense, x and y are symbols, and they play roles. It doesn't mean that they're always tied to those particular roles. And so we want to get to the point where we're comfortable saying, hey, I can think of these things in different ways. In fact, I gain power by allowing myself to say, oh, well, even though the normal convention has them playing these roles, by saying I can turn that normal convention around, that gains me power. So, with that in mind, is this a linear first-order differential equation? The answer is yes. Because, notice, we have an x prime and an x. And so, from the perspective of x as being our thing we're solving for, yeah, this is very much linear. So what we can do some rewriting here. We'll say x prime times y cubed, and I'm going to bring this across, plus 4y squared x, just I want to emphasize, something x prime, something x, equals 1. All right, great. Well, now what? Well, we need to make this coefficient be 1. Okay, so divide. So we'll have x prime plus, here, 4 over y times x, because, y squared divided by y cubed is an over y, is equal to 1 over y cubed. And we're off to the races. That was the hard part of the problem. The rest of the problem is the fun part, which says, okay, here's our p of y in our case, and let's work on that. So we get to work. So the integral 4 over y dy, oh, that's a little bit light. Let me get a slightly darker color here. So the integral 4 over y dy, well, that's 4 log y. And again, at this stage, we don't need our constant. Our constant is assumed to be 0. And so, e to the 4 log of y. Well, not surprising, the 4 goes in as an exponent. This becomes y to the 4th. So, we need to multiply everything in our equation by y to the 4th. So you get y to the 4th times x prime plus 4y cubed times x is equal to y. You might have said, we should have just multiplied this by y. Well, yeah, but we didn't see that that was the right thing to do. And that's why we had to do this intermediate step. Okay, well, the left-hand side, no surprise, it's a really nice derivative. It's derivative with respect to y, because we're thinking of y as the part that changes here, of y to the 4th times x. And that's going to be equal to y. All right, well, we're rounding the corner, so we integrate both sides with respect to y. And what do we get? Well, we get y to the fourth times x is equal to 1/2 y squared. And plus c. Or we can say, lo and behold, that says that x is equal to 1/2 y squared divided by y to the fourth. So put it as 1/2 y squared plus some constant c over y to the fourth. And there we go. That's it. Now, could we go further? Because we might be like, hey, is this okay? And the answer is, you know what? This is fine. This gives us a perfectly reasonable relationship to work with. We can do some things. And just for fun, because you're such a fun audience and you're so patient with me, I'll point out something that you can do here. Just to be like, whoa, slow it down, Steve, don't do it. But I would say that in some sense, this is kind of the best answer. Now, if you're thinking of like, wow, I really want y as a function of x, I'll show you how you can get that. But this is a nice answer too. And in some sense, this is a nice implicit answer. And by that we mean, well, we may not have it necessarily in the form y is some function of x, but we can see how it all comes together here. And so, all right, what can we do to get a more general answer? Okay, here's what we can do. Shh. Now, you don't have to do this, okay? If you don't like what I'm about to do, skip the video ahead a little bit, okay? All right, so what we can do is say, hey, look, this is the same as x y squared squared minus 1/2 y squared minus c, well, I'll just say plus c equals 0. Now you might say, well, shouldn't that be a minus c or should it be a plus c? It doesn't matter, right? Constants absorb constants. So now, what do we see here? What do we have? It's a quadratic formula, but now it's a quadratic formula where we have y squared. But that's okay. Since we have a quadratic formula, we can use the quadratic formula equation. So y squared is equal to negative b 1/2 plus or minus the square root of b squared 1/4 minus 4ac. So that's minus 4 times c times x. All that over 2a. Now, we can, of course, do some things. We can pull out this 1/4 term here. And if we do that, it comes out as a 1/2. So they both have 1/2. And so we could say, look, this is 1 plus or minus. And then it's going to be a 1/2 from here, a half from here. So that'll make a 4x downstairs. And then, what do we have? Square root of 1. And now, here's what we can do. We can have a lot of fun here. So you might say, well, we pull out a 4th. Yeah, so that should be a 16, right? But notice, there's a c. And what can c do? C can absorb constants. So we like sponge up our constants, like, wah, 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 wah. And they say, okay, aha, it's my constant sponge. And and we can even absorb the minus. So we can say plus some constant times x. And there we go. Now that's y squared. So what's y? So we can say y is the square root plus or minus of 1 plus or minus the square root of 1 plus some arbitrary constant, c times x, and all of that divided by 4x. And, okay, so there's another way that we can write the answer where we have not x as a function of y, but y as a function of x. And I would say that between the two, I kind of prefer the x as a function of y. It looks a little bit nicer. I think it does. So, but all right. I said, hey, we can do something, right? And we did. And that's what we get. Wow, what an answer. What an answer. Amazing. Amazing. All right. Well, there's that one. We should do more. The more we practice, the better we get. So let's do another one. All right. Solve xy prime equals 2y plus x cubed cosine x. Okay, great. We should be able to do that. That looks pretty straightforward. So we say, okay, let's work our process. First thing is we need to move things around. And all right, so in this case, we can move the 2y across. So x, y prime, subtract 2y should equal x cubed cosine of x. And say, okay, we have something y prime, something y, and over here just the x part. But we're not quite ready yet because that's not a 1. So we make it a 1. We divide by x. So y prime minus 2 over x y is equal to x squared cosine of x. All right, so we're ready. We're ready to begin. Well, where to begin? We have the minus 2 over x. Now remember, the minus is part of it. That's going to be our p of x. So we say, okay, great. So we're going to work with this. And so the integral minus 2 over x, well, that's the same as what? Minus 2 log of x. All right. Well, that's the same as log of x to the minus 2 power. Or, if you like, that's log 1 over x squared. So, when we talk about our integrating factor, we're going to take e to that, and so our integrating factor is 1 over x squared. Okay, so multiply both sides by 1 over our x squared, and what do we see? Well, we get 1 over x squared y prime minus 2 over x cubed times y is equal to, that's not very interesting, just cosine of x. Well, may not be very interesting, but it's good for us because we see, this is the derivative of 1 over x squared times y. And, all right, and then over here, well, we have cosine of x. And now we integrate both sides. All right, integrate dx, integrate dx, and we see that 1 over x squared times y, integral of cosine, is it sine or is it negative sine? It's sine, just a sine function. Okay, that equals sine of x, and anything else? Plus c, don't forget we need that, and clear out, we want to get y, so we say, y has the form of x squared sine of x plus some arbitrary constant c times x squared. And that's it. We're done. That's the whole thing. Wow, that was pretty quick. Cool. Nice. Nice. See, these problems aren't so bad. Once you get the hang of it, they go pretty smoothly. And here we stopped because we didn't have any initial conditions. So, all right. Well, yeah, that's a real change of pace, right? Just a few minutes. Well, all right. We'll still have a few more. Okay. 2 tanks are linked together in such a way where 5 gallons per minute of pure water constantly flows into the first tank. Then that mixes, and then 5 gallons per minute from the first tank goes into the second tank. And then that mixes, and then 5 gallons per minute goes from the second tank and goes out. Okay, so that's the setup. So let's draw our little picture here. So we have our first tank. And then we have our second tank. And then we have that. Okay, so we have stuff coming in, and then we have there, and then we have there. Okay. So that's the pitcher, and then we'll make some notes here. This is 5 gallons per minute, and this is 5 gallons per minute. And notice in particular, no changes in the total amount of liquid happens, right? The inflow equals the outflow in both the tanks. Okay, so the first part is just this pitcher. Now we have the pitcher. So then we get the second part. Okay, so we're told something. The first tank, so our first tank, initially, so we have some initial conditions here. It holds 100 gallons, all right? And notice that it will always hold 100 gallons. So it's always going to be 100 gallons at all time because the inflow equals the outflow. Okay, it holds 100 gallons and 50 pounds of salt. Now that's initially. So we'll say at time 0. And now the second tank, well, that's 200 gallons and also 50 pounds of salt. Now, you'll notice they both have the same amount of salt, but because this is a bigger tank, it's less salty than the first. And what's the question? Well, it says determine the maximum amount of salt ever in the second tank. So we should say, is this a question answerable? Probably yes, because it's asking us. Does it make sense to ask this kind of question? Well, what will happen in the very, very, very long run? Well, let's think about just here. This coming in is pure water. Now you might say, well, how do we know it's pure water? Well, because it says it right here, pure water, no salt at all. And so you always have pure water coming in, but a little bit of salt is leaving. So in the long run, what should happen to the water here? It'll become basically pure water in the, as time runs off to infinity. Which means that this is, the water coming in is also going to become pure water in the long run. So what's going to happen to this? Well, this is going to become pure water. So in the long run, this is going to have all the salt go out as well. So in the long run, we know the salt is going to go to 0. And we know it's not 0 yet. So, okay. So if it starts at something not 0, and in the long run goes to 0, then we can expect, oh, yeah, there's going to be a maximum. But we also say, hey, initially, when we look at the kind of water coming in, it's a denser concentration, right? Because this says there's 50 per 100 gallons. This says 50 per 200 gallons. So initially, this is saltier water that's coming in than what's coming out. So that says our concentration is going to go up initially, and then it's going to go down. So it says, okay, so there should be a time when we peak, our maximum saltiness. All right, good. Wow. Whew. Okay. Okay, so it's a reasonable question. and now what you see here, when I'm pausing, it's like, wow. Let's just think about what we should do here. We really should have 2 equations involved because there's 2 kinds of salts, right? There's how much salt is in the first tank and how much salt is in the second tank. And we do need to understand how much salt is in the first tank because that affects what's flowing into the second tank. So let's focus our energy on just the first tank. Okay? Let's see if we can answer that question. So we'll call that tank 1. And we'll say, look, initially S sub 1, so I'm using the subscript to say tank 1, S sub 1 of 0 is equal to 50, because that's how much salt there is initially. What can we say about S1 prime? Well, S1 prime, how much is coming in? Nothing. It's pure water. There's no salt coming in. So that's our inflow. How much is going out? Well, we know 5 gallons per minute goes out. Okay, so it's 5 gallons per minute. And then we say, well, how much salt is in there? So we take the total amount of salt in the tank, and so that's going to be S, and divide it by how many gallons there are, which is 100. So this is our concentration of salt in the tank. And so we say, oh, okay, this is the same as minus 1 over 20 times S. Whoops, subscript 1. So now we have this really nice differential equation. In fact, we probably recognize this. We've seen it before. Do you remember it? This is the same thing that shows up in radioactive decay. And also was a population model where it's like, well, instead of explosive exponential growth, it's exponential decay. And you can do this by solving a separable differential equation. So if we did that, we could, for example, say, ds1 divided by s1 is equal to minus 1 over 20 dt, or the natural log of s1. That's because you integrate both sides, minus 1 over 20t plus a constant. And so s1 is equal to some constant, e to the minus t over 20. And now, initial condition says at time 0, that we should have 50. When you plug 0 into here, well, we'll get e to the 0. So 50 equals c e to 0, which is c. And so we say, aha, the amount of salt at any given time in the first tank is equal to 50 e to the minus t over 20. All right, so there we go. There's our tank 1. Now, tank 2. So now that we understand tank 2, the reason that we talked about tank 1 is it's affecting what flows into tank 2. So let's talk about tank 2. So we have some things going on. We know initially, and I'm going to use 2 to indicate tank 2, that the amount of salt in tank 2 at time 0 is 50, same as before. And now we say, okay, S2 prime. How much is coming in? Well, the answer is we can actually come look at here, right? Because this part right here, this is out of the first tank, and it goes in to the second tank. And we know what S1 is. And so we say, oh, well, great. Well, what is this? So this is going to be this 5 over 100. This is 1 over 20. And then we multiply it by 50 e to the minus t over 20. That is how much flows into our tank. See? Because they're connected together. The amount of salt leaving the first tank has to be the amount of salt going into the second tank. Now, what is coming out? Well, it's very similar before, right? There's 5 gallons per minute going out. And now we say, well, look, what's the total amount of salt? That's S2. Divide that by 200. And so now we have something a little bit more interesting, because this 0 said, oh, yeah, things are not that exciting. But for us, it's a little bit more exciting now. Okay, so let's not get too excited with our right? We still have to do the problem. There's still a lot to clean up here. So if we clean up this says that if we look at S2 prime, and 5 goes into 200, and that's 40. So that'll be plus 1 over 40 times S2. That'll equal 5 halves, because 50 over 20 becomes 5 halves, e to the minus t over 20. All right. Next up, we need to find our integrating factor. It's already in the right form, right? There's a 1 there. So our integrating factor, it's really clean because that's a 1 over 40. And so we say, look, we'll just even write in just one line here. So it's e to the integral 1 over 40 dt, which means it's e to the t over 40. All right, so we're running out of space. Time to move up. Okay, so we're going to multiply through, and I'll skip our intermediate step and say, okay, if I multiply everything by e to the t over 40, this left-hand side becomes the derivative with respect to t of e to the t over 40 s2 equals, this other side is going to be 5 halves, and then we're going to have t over 40 and then minus t over 20. When they combine together, what do they become? Well, they're going to become e to the minus t over 40. So, all right, it's minus the 20th plus the 40th. Okay, great. Well, integrate both sides. So integrate. So, whoops, I'm going to give myself a lot of space to write down the dt's. But, okay. So, we have, this says we have e to t over 40 times s2. Now, on this side, okay, well, when we integrate that, well, the integral of e to the minus t over 40 is e to the minus t over 40, and we just got to account for that minus 1 over 40, and we do that by dividing by minus 1 over 40, or equivalently by multiplying by negative 40. So we're going to have 5 halves times negative 40, which becomes minus 100. So minus 100, and then e to the minus t over 40, and then, of course, plus c. All right, good. So we integrated. Well, let's solve for our constant. While we're here, we should solve for our constant. And how do we do it? Well, we know how much pounds of salt there is at time 0. So, if we say at t equals 0, we have that e to the 0 times 50. So we have 50 is equal to minus 100. That's e to the minus t over 40. And then plus our constant c. So we get that c is equal to 150. All right. Finally, multiply both sides by e to the minus t over 40. And we come to the conclusion that our amount of salt, S2, is going to be minus 100 e to the minus t over 20, right? So it's minus t over 40, minus t over 40 is minus t over 20, and then plus 150 e to the minus t over 40. Good. Now, that's not our answer, but I'm going to put a box here because I feel like we deserve a box. We worked hard for this box. So we should celebrate its boxiness. All right. Are we done? No, we're not done yet. We're not done yet. But we're so close. Okay. How do we finish it? Well, what are we after? We want to maximize the amount of salt ever in the second tank. And let's just point something out. That as time goes to infinity, both these terms go to 0. And so it does match our intuition. It also, if you say, well, which term is larger, this first term is a larger term. And you'll see that because of this exponent here, it's actually, because the coefficient is smaller, this goes to 0 slower than that one does. So we have both terms are going to 0, but this is going to 0 slower. So it matches with our behavior where we think it should first go up a little bit, and then it should go down. Okay. We're almost there. When will a maximum occur? Well, a maximum occurs when what's true? The derivative equals 0. So let's set the derivative equal to 0. So we're going to look at S2 prime. At this point, you're probably saying, like, what? we just solved for S2, and now you want us to go back and look at S2 prime? Ah! Oh, good times, good times. But, okay, what is S2 prime? All right, so, well, okay, we bring it down. The minus 1/20th comes down, minus 1/20th, and then we have into times minus 100. I'll make it a plus, and we'll get 5. E to the minus t over 20. And then here, okay, the minus comes down, and, well, okay, so it's 15 over 4. E to the minus t over 40. All right, well, what can we do? Well, we can factor out, well, let's factor out a 1/4, and let's also factor out, well, let's factor out an e to the minus t over 40, right? Why not? We need to pull this out. Okay, so I just point out 1/4 just because I don't like fractions. We'll have e to the minus t over 40, and then what's left? Well, from here, we'll have 5 e to the minus t over 40, because, we pulled out a little bit, and then minus, we should have pulled out a 5, shouldn't we? There we go, yeah, 5/4. So that's just a 1, and then minus 3. All right, so we take the derivative, and that's what we get. What do we do with this derivative? When we're looking for a min or a max, we then set this equal to 0. Well, what do we know? This part can't be 0. Can't happen. Wouldn't do it. Wouldn't do it. All right. So what do we do? Well, now we come to this part. Say, look, that part has to equal 0. So we say, aha, e to the minus t over 40 has to equal 3. Now, I'm not going to keep going too far with this computation, but what does that tell us? Does this give us the maximum amount? No. What does it give us? It gives us when our maximum will occur. And here's the cool thing. We're going to be able to take this and get the answer that we need. Okay, so hopefully, if we haven't made too many mistakes, then life will be good. All right, so what's our way to finish up? Oh, wait, whoops. I see I did make a mistake. So let me correct myself. Can you see my mistake? You've probably been screaming, Steve, you've been making a mistake. Notice I pulled out a 4th here. What should be here? Because there wasn't a 4th to pull out. Since there wasn't a 4th, this should actually have been a 4. So this is not 3. This is 3/4. Okay, that was my mistake. All right. So that says, for the value of t, where e to the minus t over 40 equals 3/4, that is the time when we're going to have the maximum amount of salt. So we're going to take that and put it back into S2. So how do we do it? Well, the way we do it is we say, okay, look, how does this e to the minus t over 40, that becomes a 3/4 there. What happens to this? Well, what's the relationship between e to the minus t over 40 and e to the minus t over 20? Well, I have to double, if I double this, I end up with this, which really the way I double is square. Right? So if you were to square this, you'd get e to the minus t over 20. So I get 9/16. So that says at the optimal time, we get that S2 is minus 100 times this 9/16. That's at 3/4 squared, plus 150 times 3/4. And, okay, cleaning up a little bit here. Now, 100 is divisible by 4. And so we can say, okay, 100 divided by 4 is 25. 9 times 25 is 225. So let's just... So we have S2. So that's going to be minus 225 over 4. All right. That's the first term. And then plus 450 over 4, which means our final answer, these are pretty easy to combine, is 225 over 4. That's it. In case you're wondering, in terms of decimals, that is 50 point, right, 50 would be, oops, not 50, 4 into 200 is 50, and then you can do a little bit more. In fact, if you look at this, this is really 224 plus 1 over 4. 224 is 56, and so it's 56.25. So that is our maximum amount of salt. So it starts out at 50 pounds of salt, goes up to 56.25 pounds of salt, and then in the long run goes to 0. Oh my gosh. Whew. We deserve a pat on the back for this one. Okay, good job, us. All right, 2 pats on the back. Double patting. Nice. This won't be on the exam. But it shows you that it is possible to do things. And there's a process here. There's a methodical process. Take your time. Don't panic. And just think about the pieces. Build up to an answer. And it also shows that even though we haven't been doing very much, we're able to answer some pretty sophisticated questions, and which is amazing. And we're going to get better. We've only just begun. Amazing. Amazing. Wow. I think it's safe to say that's the hardest problem that we might have to see today. I'm pretty sure that's pretty safe to say. All right, we still have a few more problems. All right, so back to a nice cooling down problem, right? So solve 1 plus t squared times y prime plus 4t times y is equal to 1 over 1 plus t squared squared. All right, well, that doesn't sound so bad. You can already feel like, oh, Steve, I see where you're going. I know you like your arctangent. I do like my arctangent. It's true. So maybe there'll be an arctangent here if I'm lucky. Where do we go? Well, first off, there's this 1 plus t squared in front of the y prime. That's not good. So we need to make it a 1. So we divide everything by 1 plus t squared. So we can say, all right, y prime plus 4t over 1 plus t squared y is equal to 1 over 1 plus t squared cubed. Now, you might look at this and say, oh my gosh, I have to integrate 1 over 1 plus t squared cubed. And no, come on. First off, we have to do our integrating factor. So we say, okay, that piece here, this is our p of t. So we're going to integrate. So we integrate 4t over 1 plus t squared dt. All right, well, let's see. U equals 1 plus t squared. Du would be 2t dt. And very conveniently, 4 can be thought of as 2 times 2. So we have a 2t. So this becomes the integral of 2 from that 2. Then the 2t dt becomes du, and a 1 over u. I will say you'll see this happen a lot for problems involving the method of integrating factor, where you're like, wow, I'm getting lots of logs showing up. And the reason that it happens so often is to get a pretty simple integrating factor, it kind of has to. We have to end up with something where we have e to that be a nice expression. And so for us, okay, so that's 2 log u. Again, the plus c, we choose c to be 0. Well, u is 1 plus t squared, and the 2 can go inside the log. So this is log of 1 plus t squared squared. So, say, aha, our integrating factor is e to that. And we say, all right, well, great, we can do that. That's just 1 plus t squared squared. So now we go back to our equation. Everything gets multiplied by 1 plus t squared squared. So we're taking our whole equation and we're multiplying by 1 plus t squared squared. And what do we get? Well, we get 1 plus t squared squared y prime plus 4t. And here we get one of the 1 plus t squareds to cancel. So 1 plus t squared y is equal, and over here, well, we still have a single 1 plus t squared left. Now, this, by design, it's set up so it works this way, is the derivative of something, namely our integrating factor and y. And you can check, right? Take the first times the derivative of the second, that's y prime. Now take the derivative of the first. 2 comes down, 1 plus t squared, times the derivative of 1 plus t squared, which is 2t. 2 times 2t gives us 4t. Yeah, so this is, in fact, the derivative that we claim it is. All right, and that should equal 1 over 1 plus t squared. And now we're ready for the next step, which is to say, hey, let's integrate these two sides. Left-hand side, very easy to integrate. By design, yes, of course. Right-hand side, by design. This is arctangent, one of our favorite integrals. Oh, what a lovely integral. And of course, remember there's a plus c. And now we're basically in the home stretch. I say, okay, get y by itself. So y is equal to arctangent of t. Divide that by 1 plus t squared squared. And then don't forget there's a plus c. And divide by 1 plus t squared squared. You should always have, when you're looking at a general solution, there should be a plus c when you're doing a first order equation here. So if you didn't have that, you should be very suspicious and be like, whoa, I am very suspicious about what's happening here. All right, great. Wow, good. A little bit of change from our previous problem, right? We were able to actually finish this one on a relatively short amount of time. A 25-year-old ISU graduating senior accepts an engineering position with a salary where the salary behaves as this nice function. So S for salary. 50e to the t over 30k. So k is 1,000. So that means at time 0, it's 50,000. So okay, you start at 50,000, but it keeps going up. And it's the best kind of growth. exponential. We like exponential growth when we're talking about money, especially when it's money coming to us, not money that we have to pay. All right, so they're making a fair amount of money, especially, as they go on further in their career. Okay, the graduate has a retirement plan that grows at a rate of 5% continuously, and also 10% of the salary is deposited into the retirement plan. Determine the amount available for retirement, not then, should be when the graduate reaches the retirement age of 70. Okay, all right. Well, great. Let's figure this out. So what do we have? Well, so we have the retirement. So let's call R how much money we have saved for retirement. Now, initially, how much money do we have when we start? Well, nothing. We haven't started our retirement plan. Okay, so that's some initial condition. That's not looking too promising. We may not want to retire on that, but that's okay because we have time. So how does our retirement change? Well, in this case, the retirement actually has two things happening, and they're both good things. They're both going up. So one thing that's happening is that there's this sort of natural rate of growth of 5%. So that means that however much money you have in your retirement plan, 5% naturally just sort of comes back to you as additional new retirement. So 5%, also known as 1/20th. So this is your 5% return, is what's happening here. And then, in addition to that, we say, look, plus there's 10% of your salary. Well, how much is your salary? That's up here. So 1/10 of your 50 e to the t over 30. And we'll have our retirement, and we'll make it in terms of thousands, so that way we don't have to add lots of zeros everywhere. And at the end, we'll just say, remember, that's how many thousands that you have. Okay, and so this is your 10% contribution. And so that's what's happening to the retirement plan. Okay, now we're ready to go. We have it. We see all the effects that what's happening to the retirement. That's been accounted for. And life is good. So let's get to work. So first thing, we do a little bit of rearranging. Say, hey, this is the same as what? R prime minus 1/20 times R is equal to, 5 e to the t over 30. And, all right, what's our integrating factor? Well, we've been doing it so much, we should hopefully get really good at it. It's going to be e to the integral of p. Well, p is just a constant here, minus 1/20 dt. Okay, so that's e to the minus t over 20. All right, so there's our integrating factor. Beautiful, great. We've got this in the bag. All right, so multiplying both sides by this e to the minus t over 20, we say, all right, so we really have the following. E to the minus t over 20 times r prime minus 1/20 e to the minus t over 20 times r is 5 e. And now, all right, got to do a little bit of work here. What do we have here? Do a little side computation. We'll do it down here in the corner, all right? Because we're going to multiply. So we're going to have 1/30 subtract 1/20, right? T over 30 minus t over 20. Well, let's think of this in terms of 60ths. So we have 2/60ths subtract 3/60ths, which is minus 1/60th. All right, so we have e to the minus t over 60. All right, good. Well, we're in business because the left-hand side is something pretty straightforward. E to the minus t over 20 times r. And the right-hand side is not so bad. Not so bad at all. Okay, so at this stage, we turn to integrating. So we integrate both sides. Integrate and integrate again. All right, so what do we have? Well, okay, we get e to minus t over 20 times r. On this side, well, what happens? We're going to get, again, e to minus t over 60. But then we need to divide by negative 1 over 60, which is the same as multiplying by negative 60. So minus 300. Woof, that's a big number. Plus, of course, some constant c. Now, how do we solve for c? Well, we know how much there is at time 0. So we can say, look, at time equals 0, we can say 0, there's no retirement, is minus 300 plus c. So c equals 300. All right. Well, let's put this together and say, all right, so our retirement at any given time, well, we need to move this across. So you're multiplying by e to the t over 20. So that would be minus 300. Well, okay, so if you have 1 over 20, and then you subtract 1 over 60, what would you have? You would have e, so this would be, so again, we're multiplying by e to the t over 20. So it's 1 over 20, which is the same as 3 over 60. Subtract 1 over 60, which is 2 over 60, or 1 over 30. So it's e to the plus t over 30. And that's looking bad, because that's minus 300, and that's growing exponentially. But we also have plus, and then c is 300 e to the t over 20. So this grows faster than that. So in the long run, we're coming out ahead. All right, so this exponential term dominates that exponential term. Now that's our retirement at any given age. What age do we care about? Well, at age 70, but that doesn't mean we plug in 70, right? It's because we're talking about since we started. We started at 25. So what we need to do is plug in 45. So 70 years old, that corresponds with time t equals 45. And so we say, okay, great. Our retirement at age 45 would be minus 300 e to the 45 over 30, and then plus 300 e to the 45 over 20. All right, is that good? Well, this is the time to go ask a calculator. So I'm going to go grab a calculator, and I'll come back, and we'll continue our discussion. And we're back. Okay, so how did our engineer do? Did they have a good amount of retirement? Well, so you plug this in, and you say, aha, this is approximately 1501.81K. But remember, that means thousands. So that's 1.5 million. So yeah, our engineer did pretty well. I mean, that engineer definitely is going to be getting a lot of phone calls from the Alumni Association saying, hey, we could use your contributions. Please contribute your money and to the alumni, right? Yes, something for you to look forward to once you graduate. Aha. Well, maybe it's not necessarily something you look forward to when you graduate, but it's coming. It's coming. I want to do one last problem, and because we need more practice with doing a certain thing. Not necessarily because it's going to show up a lot, but because it's been a while. It's good for us to practice, and so we're going to do it. We're going to do it. Okay, so solve y prime plus 2 over t times y is equal to e to the t. Okay, Well, that doesn't seem so bad. Kind of feels a lot like things that we've done before. And we say, look, they made it super easy for us. It's even in the right form, right? So here's our P of t. So we can say, look, our integrating factor, we can even do that in one step here because it's pretty straightforward to integrate that, which is e to the integral P of t dt. All right, that's e to the integral of 2 over t dt. Well, okay, so that's not bad to compute. That's 2 log t. But of course, the 2 can come in as an exponent. So that's e to the log t squared, which is t squared. Okay, great. So it's t squared. All right, that's our integrating factor. So we multiply everything by t squared, and we say, all right, t squared y prime plus 2t times y will equal t squared e to the t. And the left-hand side, well, yeah, that's not so bad. That's really the derivative with respect to t of t squared times y. And now we have, on the other side, this t squared e to the t. And we're saying, hey, wonderful. We've made great progress because we've made great progress. We just need to integrate both sides. And as always, left-hand side, very straightforward. So we end up with our t squared times y. The right-hand side, well, not so much. We're going to have to do some work here. And what do we need? Well, we're integrating t squared times e to the t. How do we integrate something like t squared times e to the t? What's the right procedure here? And the answer is integration by parts. And so this is just a chance for us to do a little bit of integration by parts practice here. And of course, it's good for us to do that. Like I said, we will see some integration by parts as we go along. And so it's good to get those gears moving again so that by the time we really need it, we're like, yeah, we're pros at it by now. Come on, give us a break. So when we're doing integration by parts, we have two parts. There's something that we want to integrate and something we want to differentiate. Now, e to the t, it doesn't really matter whether integrate or differentiate. It's e to the t. It's one of the reasons we like e to the t. So we say, okay, well, let's not worry about that. Let's think about the other piece, which is t squared. We integrate it, we get to t cubed. We differentiate it, we get to t, with some constants involved. Say, ooh, let's differentiate that part, because that makes things simple. One of the underlying philosophies when you're looking at a math problem is, how can I make my problem simpler? Because we like things to be simple. Simple means we have a good chance that we can actually solve. So we're going to say, all right, we'll let this be the u part, and this will be our dv part. So du will be 2t dt, and v will simply be e to the t. So according to integration by parts, this will be u times v, which will be t squared e to the t, minus the integral of v times du. So that'll be, all right, 2t e to the t dt. And what do we do here? Well, no surprise, it's integration by parts again. And there's another philosophy which says we could go through the same dialogue, but another philosophy says once you make a choice, you stick to it. You don't say, I changed my mind. I'm going to, the part where I differentiate, now I'm going to switch to have that be integration. No. That just gets you back to where you start. That's not making progress. That's sending you back. So we're still going to have the e to the t dt. That's still going to be our dv, and this other part will still be our u. All right. Well, all right. That's not so bad. du 2 dt, v is e to the t. Now here's the part where it's easy to make a mistake. Do you see that this minus here? You have to remember it's minuses everything. So we're going to put in a point-saving device called a parenthesis. Parentheses are very cool at helping us keep track that, oh yeah, that minus goes through. Let me not forget that. and I want to get all my points because I like getting all my points. That's a goal of ours. All the points. All the points. Okay, so we have uv, so that'll be 2t e to the t minus v du. So integral v du to e to the t dt. Okay, so remember the minus comes through. And we say, okay, so what do we have? We have t squared e to the t minus 2t e to the t. Minus minus makes a plus. And the integral of 2e to the t is 2e to the t. And of course, don't forget a plus constant c. So that is what comes over here. So we have t squared times y is equal to t squared e to the t minus 2t e to the t plus 2e to the t plus c. Finally, to solve for y, because that's what we're after, divide everything by t squared. And so we can say our answer is t squared e to the t divided by t squared is e to the t minus 2 over t e to the t plus 2 over t squared e to the t plus some constant c over t squared. And there we go. All right. Oh my gosh, we've been here for a while. I think we have definitely earned a break for a short time, but we have other things we have to talk about. So come back next time and we'll continue on. Have a great day.